Outcome 1, Lesson 3, Electric Fields. Part 1, Fields. We're going to start this lesson by looking at the general definition for a field. There are two types of forces in nature. Contact forces, in which the object exerting the force is in actual physical contact with the object that's experiencing it. This is any time you have a physical push or a pull, and other forces we have examined in the past, like the normal force and friction, are examples of contact forces. There are also action at a distance forces. For action at a distance forces, the object that is exerting the force does not directly contact the object that is experiencing it. These are forces such as gravity, electrical forces, and magnetic. In all three of these forces, they can exert forces on other objects without actually touching them. For these kinds of forces, we need fields to explain them. A field is an area in space around an object that can influence or exert forces on other objects. Sometimes we refer to this as a force field. For example, objects near or on the Earth experience a gravitational force because they are in Earth's gravitational field. For example, a person located at this point on the Earth would fall towards the center of the Earth along the gravitational field, or an object on another location would also fall towards the center of the Earth. These two directions are different, but they both point towards the center point on the Earth due to Earth's gravitational field. A force is a real thing. We can feel, measure, and observe forces. A field, on the other hand, is a mathematical model. It exists to explain these action at a distance forces. The concept of a field was created by scientists to explain and predict observations, but it can't actually be felt, measured, or observed directly. Part 2. Field lines and direction. Electric, gravitational, and magnetic fields are all vector fields. This means that they have magnitude, which is the amount or a number part, and they have direction, or the way that that field points at that location in space. The magnitude and direction of a field varies depending on the point in space. For example, Earth's gravitational field. If you're on the surface of the Earth, you'll feel a gravitational field equal to 9.81 meters per second squared. This is because Earth's gravitational field is stronger at the surface of the Earth. If you're further away from the surface of the Earth, this gravitational field amount will change. For example, at the blue dot I've put in here, the gravitational field might be more like 8 meters per second squared. It decreases as you get further away. This is because the magnitude of a field varies depending on location. You'll also notice that the direction is different too. The one on the surface of the Earth points towards the center of the Earth, and the one further away also points towards the center of the Earth, but the two arrows point different ways because of their location with respect to the center of the Earth. The direction of a field also varies depending on the point in space. The direction of a gravitational field is always towards the center of the object. The magnitude decreases the further you are away. In the diagram, we can see that the lines, these are called the gravitational field lines, are closer to each other when they're at the surface than when they are far away. This is called the field line density. The field line density tells you the strength of the field at that location. The closer the lines are together, the stronger the field is at that location. Electric field lines. The electric field lines point in the direction that a positive charge would move if it were placed in that field. It's important that you remember that it's the direction of a positive charge. Now, with gravitational fields, it didn't matter because there's only one kind of gravitational object, a mass. But in electricity, we have positive and negative charges. Electric fields are defined by positive charges. So, electric field lines point towards negative charges, and they point at the center of the charge, because this is the direction a positive charge would go if it were placed at the point in this field. Electric field lines always point away from positive, because positive repels positive, and if I were to place a positive charge at that location, it would move away from the center of the positively charged object. The density of the field lines tells you how strong the field is. The closer the lines are together, the stronger it is. Density refers to how close the lines are together. So you can see in this picture, the charge that is worth twice as much has twice as dense lines surrounding it than the single charge. There are some common electric field configurations that you're going to need to be able to remember for tests. Electric field near a single negative charge points at the charge. Remember that the electric field is the direction that a positive charge would go if it were placed at that location near the charge. You should also know the electric field near a single positive charge, which is away, because positive repels positive. The electric field near two negative charges is a little bit more complicated. On the outside of the charges, it looks about the same. It points towards the negative because that's the direction a positive charge would go. But between them, the positive charge gets confused about which way to go, and it has a bit more of a curved path. As it approaches the two charges, it swings in as if it's attracted to one, but ends up going to the other. In the middle, between the two charges, there's a dead zone, where if you were to place a single positive charge, it would be equally attracted to either of them, so there's no electric field there because the electric field lines cancel each other out. Near two positive charges is similar. Positive charges have electric field that moves away from them because positive would repel a positive charge if it were placed there. Between them, if I was to place a positive charge, we would find that it swings out, sees the other one, and makes a curved path, trying to get away from both of them. And we can see again in the center, there's a spot where it's equally repelled by both of them, and so there's no electric field there because the electric field lines cancel each other out. The electric field near a negative and a positive charge is the final configuration you should be able to identify. Since positive is attracted to negative and repelled from positive, the lines between a positive and a negative charge point directly from the positive to the negative. If I were to place a positive charge in that location, it would swing around and get to the negative. As we move further out, they point exclusively at the negative and away from the positive. Inside a conductor, the electric field is quite unique. Since electrons always distribute themselves into an equilibrium position, evenly spread out across the surface of a conductor. Because of this, the electric field of the electrons completely cancels each other out inside a conductor, and the electric field inside a conductor is zero. So, for example, if you have a large spherical conductor, we know that the electrons will evenly spread themselves out, equally spaced along the surface. Because of this, the electric field pointing towards one electron is completely canceled out by the electric field pointing towards another electron on the other side. And as a result, the electric field completely cancels itself out in all directions. So the electric field inside a conductor is zero. There's no electric field inside a conductor, no matter what. This is the starting point for something called a Faraday cage. A Faraday cage is a conductor that you can place objects or people inside, and since the electric field is zero inside it no matter what, the person or object is protected from electrical charges. So if you're ever in a lightning storm and the lightning looks like it's about to hit, if you can climb inside a large metallic object like a conductor, you'll be protected. Like, for example, crawl into your car. Part 3. Electric field calculations. Electric fields can be treated mathematically. The symbol we use for electric field is E with a vector arrow over top of it. Be really careful when you're writing this. E with an arrow over it is electric field. E without, or E that is not a vector, refers to energy. These two are completely different things, so it's important that you're careful not to confuse them. The unit for electric field is the Newton per Coulomb. And one more reminder should be that you always remember that electric fields point towards, negative, and away from positive. This will allow you to find the direction of an electric field. There are two formulas we can use for doing electric field calculations. For the purpose of these formulas, I'm going to write down what some of the symbols are going to mean. E, as shown above, is the electric field in question. Fe is the electric force on a charge in that field. Q is going to be lowercase q, is a charge in the field. This is going to be different from capital Q, which we're going to use to refer to the charge that produces the field. The first formula is found on your formula sheet. The electric field is equal to the force on a charge in the field divided by the magnitude of the charge placed in that field. This isn't a really useful arrangement, but it's what appears on your formula sheet. I find it more useful to rearrange it and write it as Fe equals EQ. This is a more useful rearrangement because it allows us to calculate the force of a charge in a field. The second formula isn't on your formula sheet at all. It's expected that students in Physics 30 will be able to derive formulas by themselves. Deriving means combining two formulas to create a whole new formula. So to derive the second formula, we use electric field equals Fe over Q as our starting point. And then we remember Coulomb's law, which says that the electrostatic force on a charge is equal to Coulomb's constant times the two charges, these are the charge that produces the field, and the charge that's in the field, divided by the distance between them squared. So this could be rewritten as electric field equals KQ over R squared divided by Q. But we see the charge that's in the field is on both the numerator and denominator of this formula, so it can cancel out. This leaves us with the electric field is equal to Coulomb's constant times the charge that produces the field divided by the distance from that charge squared. This formula is very useful to determine the magnitude of the field at a particular point in space. R refers to the distance from Q in this case. Now remember that this formula will only give you the magnitude. You need to determine the direction yourself, remembering that direction is always towards, negative, and away from positive. We'll use this formula in a minute, but I want to show you gravitational fields, which you learned last year in Physics 20, so you can see the parallels between these formulas. Gravitational fields are given by the symbol small g. The unit we use for gravitational field is the meter per second squared, but we could also use the unit newtons per kilogram, which is similar to the newton per coulomb, which we use for electric fields. I'm going to show you that these two are actually equivalent. Since a newton is a kilogram meter per second squared, and a newton divided by a kilogram cancels out the kilogram to be just a meter per second, we could write the unit for gravitational field as either a meter per second squared or a newton per kilogram. Either one works. There are also two formulas for gravitational fields. You're probably already familiar with F equals mg, or the force due to gravity on a mass in that gravitational field is equal to the mass times the gravitational field. This is equivalent to Fe equals QE, where instead of mass we have charge and instead of gravitational field we have electric field. For the purposes of these formulas, I'm going to use F to be the force on a mass in the field at that location. M is the mass in the field. And I'll use capital M to designate the mass that's causing the field. This would be something like the Earth or the Sun or whatever it is that the little m is orbiting around. And of course, little g is the gravitational field magnitude and direction itself. So we have F equals mg. The force on a mass of the field equals the mass in the field times the magnitude of the field at that point. Now, we can also derive a second formula. Since F equals mg, we can rearrange this to get g equals F over m. And we recall Newton's law of universal gravitation tells us that F equals g, the mass that causes the field, times the mass in the field, divided by the distance between them squared. This rewrites to be g equals gmm over r squared divided by m. And since the mass that's in the field appears in both the numerator and the denominator of this derived formula, it cancels out, and we get the gravitational field at a particular location in space is equal to capital G times the mass that creates the field divided by the distance from that mass squared. So you can see that this one is quite similar to the formula we derived before for electrical fields, where electrical fields is equal to K, the charge that produces the field, divided by the distance from that charge squared. So gravity and electrical fields are really similar. The biggest difference between gravitational fields and electrical fields is that gravitational fields have one direction only. The direction of a gravitational field is towards the center of the object. This is because gravity has attraction only, it doesn't have repulsion. Electrical fields could either be towards the object or away from the object, depending whether the object producing the field is negative or positive. Example: a scientist wants to know the magnitude and direction of electric field at a point in space. To measure it, the scientist places a 0.2 kilogram mass with a charge of positive 0.75 coulombs in that field. The mass accelerates to the right at 9.5 meters per second squared once it is released in the field. To calculate the electric field at that point, we need the force. Force can be calculated with Newton's second law, F equals ma, where the mass is 0.2 and the acceleration is 9.5. This gives us a force of 1.9 newtons experienced by that mass in the field. The electric field at a particular point in space is equal to the force divided by the charge that experiences that force. This is 1.9 divided by 0.75, the magnitude of the charge, which gives us 2.5 newtons per coulomb. Now we need to figure out the direction of the field as well. Since this is a positive charge and it's accelerating to the right, and the definition of electric field direction is the direction a positive would go, we know that our positive charge traveling to the right tells us the direction of the electric field. Since it's positive and the electric field is the direction a positive would go, we assume the electric field is the same direction as the direction our positive charge goes, which is to the right. We're going to do a second example using a negative charge so you can see the difference. What will be the force on a negative 0.3 coulomb charge placed in the same spot in the field? Since we know the force on electric charge equals the charge's amount times the field at that location. We already know the magnitude of the field at that location. We calculated it in the previous example. So we have 0.3 times the magnitude of the field. Now I didn't put the negative in for the negative 0.3 because this formula only gives us the magnitude and not to the direction. We're going to need to determine the direction on our own, so I left the negative out so it won't confuse us. This gives us 0.76 newtons, but we have to figure out the direction. Since the electric field direction is the direction a positive would go, so right is the direction a positive would go in that field because the field is to the right. And we are dealing with a negative charge. A negative charge would go the opposite direction to the direction that a positive would go. So we know that our negative charge would experience a direction to the left. So the force on the negative charge is 0.76 newtons to the left. Example: what is the electric field halfway between the charges in the diagram below? The charges are 5 meters apart, so the halfway point between them is at 2.5 meters. To calculate the magnitude of the electric field at this point, we need to know the electric field due to the 7.5 and the negative 3 coulomb charge and then combine it. We'll start with the 7.5. We want to know the electric field at a point 2.5 meters away from the center of the 7.5 coulomb charge. We know that this is a positive charge and electric fields point away from positive charges, so we know whatever magnitude we get, its direction is going to be to the right. So, electric field equals kq divided by distance from the charge squared. K is 8.99 times 10 to the 9. Q is 7.5. And the distance is 2.5. Watch this squared. It's a really common habit to forget to square our radiuses, which gives us an electric field equal to 107.88000000 newtons per coulomb to the right. There's a second charge there, and that's the negative 3 coulomb charge. Since it's negative, we know that the electric field at a point that is 2.5 meters away from it is going to be towards this charge. Negative attracts positive, and electric fields are the direction that a positive charge would go. So, in this case, the electric field is going to point at the negative 3 coulomb charge, which means also to the right. We can calculate the magnitude of the electric field using electric field equals kq over distance from the q squared, which is 8.99 times 10 to the 9 times the charge divided by the distance to the charge squared. You'll notice I didn't put the negative for the negative 3 in, and that's because this formula will give us the magnitude, and it's up to us to determine the direction, and I didn't want to put the negative in because then it might just end up confusing us. This gives us a magnitude of 431520000 newtons per coulomb, and so we've already determined the direction to be to the right. Now we have two vectors, both pointing to the right, so to get the total magnitude, we would add these two vectors together. So the electric field total would be equal to the electric field of the 7.5 combined with the electric field do the negative 3. This means we add our two electric fields together because they're both going to the right, and this gives us 1.5 times 10 to the 9 newtons per coulomb to the right. The vector addition gets a little bit more difficult once we throw angles into the mix. For example, what is the electric field at point A in the diagram below? So we're interested in finding the electric field at this point. It's near a negative and a positively charged object. Now we can see the electric field will point away from the positive 2. Away would be up. And it's going to point towards the negative, which would be over to the right. I'm going to number our two charges, charge 1 and charge 2, to make our math a little bit simpler to write out. We'll start by calculating the electric field due to the first charge. We'll call this E1. This is kq over r squared, which is 8.99 times 10 to the 9 times the magnitude of the charge. This is 4 microcoulombs, which is 4 times 10 to the negative 6 coulombs. Again, I didn't put the negative sign in because I didn't want to confuse the calculations, because direction is determined by us after the fact. The distance is 2 meters, so it's divided by 2 squared, which gives us E1 equals 8990 newtons per coulomb. And we've already determined the direction to be towards this negative 4 microcoulomb charge, which means it's to the right. The electric field of the second charge is going to be calculated as well. This is E2, which is kq over r squared, which is 8.99 times 10 to the 9 coulombs constant, times the charge, which is 2 microcoulombs, which is 2 times 10 to the minus 6 for micro, divided by the distance to this charge, which is 3 squared. So the electric field of the second charge at point A is 1997.7 repeating newtons per coulomb. And in this case, this is up. And it's up because the electric field moves away from the 2 microcoulomb charge. The last step is to combine these two using vector addition, but because up and right are perpendicular to each other, we need to use perpendicular vector addition. So the magnitude of the total electric field, we put this in absolute value signs to show that this is the magnitude without the direction, will be given by the root of electric field of 1 plus the electric field of 2, both squared, Pythagorean theorem, which gives us the root of 8990 squared plus 1997.7 repeating squared, which gives us a magnitude of electric field at this point in space equal to 9,209 newtons per coulomb. The direction is going to be an angle, probably somewhere off like that. The direction, theta, is given by tan -1. We're going to go up over right, so 1997.7 repeating up, divided by 8990 to the right. And this gives us an angle of 12.5 degrees, and we'll call this up of right or above right.